To AP Chemistry. This is your tutor Venkata, and today we'll be covering a review of important discoveries about the atom and some definitions that you'll need for future lessons. So the very first definition that I'll be talking about is down here, and it is known as an element. An element is a substance that cannot be chemically broken down into simpler substances. For example, an element that you actually are breathing right now is oxygen gas. Oxygen cannot be chemically broken down into simpler substances. You cannot take oxygen and you cannot chemically break it down into another element. For example, you can't take oxygen and then produce iron out of it. And this is a fundamental reason why alchemy is wrong. Prior to this, alchemists thought that you could perhaps convert, let's say, lead into gold, which would be turning Pb into Au, which does not make sense as a substance cannot be chemically broken down into a simpler substance if it is an element. All right. The next definition is a compound. A compound consists of two or more distinct elements chemically bonded together. So for example, a very famous compound that all of you probably know about is H2O, and it's H2O. It is water. It is a compound that all of us drink every day. And as you can notice, it has two distinct elements that are chemically bonded together. It has hydrogen, and it also has oxygen. So there are two distinct elements that are chemically bonded together. A molecule, on the other hand, only consists of two or more elements that are chemically bonded together. There is no mention of the elements needing to be distinct. So for example, you have H2O up here. H2O is a molecule because it has two or more elements, chemically bonded together. For a molecule, they don't have to be distinct. So H2O is a molecule and a compound. But for example, you could consider something like O2. O2 is the gas that you breathe in every day, and you are breathing in right now. It is oxygen gas. It is a molecule because it consists of two elements, two oxygens, that are chemically bonded together, but they do not have to be distinct elements for a molecule. And since O2 does not consist of two or more distinct elements, it only consists of two O's, then it is not a compound. Not a compound. All right? A mixture, on the other hand, consists of two or more elements mixed together. They don't have any chemical bonds holding them together. And a very high-level overview of what a mixture could be is, for example, a pizza. A pizza consists of several parts. For example, there is the dough, which consists of a bunch of ingredients. And the pizza also consists of its sauce, which also contains a bunch of elements and ingredients. There is no chemical bondage between these parts, so you can separate them using physical means. Although it would be difficult, it is theoretically possible to separate a pizza using physical means. Alright? So this brings us all the way back to 1774, when a man named Antoine Lavoisier came up with the law of conservation of matter. So this is a law of conservation that you've probably heard about many, many times in the past. I've learned about it since 7th grade. It teaches that in a chemical reaction, there is zero mass or matter created or destroyed. So this is a definition specific to chemistry. You might have heard the definition where there is no matter or that is created or destroyed. But for our purposes, since this is a chemistry class, I will be discussing specifically chemical reactions. So in a chemical reaction, there is no matter created or destroyed. All right? This brings us next to 1799, when another guy called Joseph Proust, he came up with the law of constant composition. He said, basically, in each pure chemical compound, there is the same percentage composition of each element by mass. So in each pure chemical compound, so for example, you have H2O, which is one of our compounds that we just learned about, right? It has the same percentage composition of each element by mass. So hydrogen will always have the same mass, the same percentage of mass in H2O in every single pure chemical compound of H2O. So for example, and this is an example, in compound A, if element A consists of 50% of the mass, and you take another sample of compound A, element A in that compound will also take up 50% of the mass because the same element takes up the same percentage composition every single time you find the same pure chemical compound. All right. This brings us to arguably the most important thing in this lesson, which is John Dalton's atomic theory. This was created from 1803 to 1808. And obviously this is a science class, this is not a history class. So 1803 to 1808 is just for establishing a chronology in your mind to try and help you understand when these discoveries came about. But you do not need to remember this unless you're trying to impress your FRQ grader. Alright, so his theory proposes three main points. The first one is that all matter is composed of tiny indivisible particles called atoms that cannot be created or destroyed. So this is true so far as we know, right? And his second proposition states that each element has atoms that are identical in all of their properties. This is actually something that has been proven false. So elements do not have atoms that are identical in all of their properties. And this is something, this leads to something known as isotopes. Isotopes were discovered, and this is actually one of the prime reasons why this proposition, the second proposition, is wrong. In a future lesson, I will go over exactly what an isotope is and why they proved John Dalton's atomic theory's proposition number 2 wrong. But for now, you can know that isotopes do prove it wrong. The third point, however, says that chemical reactions are rearrangements. And this is arguably one of the most important things that you'll need in this entire class because everything else is built on this. Instead of believing that you're destroying something and creating something new in a chemical reaction, you can simply think of it as a rearrangement. You might have a bunch of atoms organized in one way before the reaction happens, and after the reaction happens, they are rearranged such that they create a new organized arrangement. And this entire thing occurs in small whole number ratios. So whenever you're looking at a chemical equation, and when we'll talk about balancing them later on, you'll notice how small whole number ratios are used for these rearrangements. And we'll see this in a bunch of equations. For example, off the top of my head, I can think of the combustion of methane or the autoionization of water. And don't be confused by these big words that I'm throwing around here. You'll learn exactly what each of them means later. Alright, so that's all there is for now, and I'll catch you the next lesson then. Bye-bye.